All right, we are live and going. Hi everyone, thank you for coming. My name is Lars Albertsson. I'm the founder of Skling, a small data engineering startup. I'll tell you at the very end what we do. First question, how many people were here yesterday attending my talk? Okay, about half of you. I hope that you will get value for time. There's just like 3-4 slides duplicated, so we'll talk about other things. Yesterday, we talked about what has been working well for companies that have succeeded with data engineering, the history. Now we will look at the future, and there's some overlap in between, but not so much. This was a very fun but also challenging talk to prepare, because how do you predict the future? And I could stand here and say, oh, this is my favorite thing. I'm really fond of Scala. I think that's much better than Python. And that may or may not be true, that it will become popular, but I have no real fundament, no real reason for saying that. That would just be an opinion, right? Everybody can say, here is my favorite thing. I think this is going to be really popular in the future, but that's useless as a prediction unless you base it on something more. And to the right here is experts' predictions on solar power installations, and the lines there are the what the experts thought would happen, and the black line is what actually happened, right? So the world is full of crappy predictions from experts. So don't believe them unless there's reasoning behind it. So I will try to predict the future of data engineering in some aspects where I believe that I can argue for some reason that it is likely to become the future. And I will go into that arguing a lot so that you can judge for yourself and perhaps get a few new tools to predict the future. And I have way too many slides, I'm sorry. I tried to kill my darlings, but I couldn't. So I'm going to go fairly quickly through this presentation. But if I'm completely incomprehensible, like stop me, and we'll pause down and slow down a bit and go into deeper detail so that I'll be comprehensible. How do we predict the future? I used to work for a company for a little while where we actually try to predict the future, and there are a couple of ways that you can do. At the time, that company, we were looking at promises, what people had said would happen in the future. And so this is an example. Somebody said there will come a train at this particular hour, and the train usually comes. Did you know that there were trains in Gotland, by the way? I didn't know until recently. Another technique is extrapolation, right? What has happened, and you can continue that further, and this is one of the most efficient extrapolation. This is Moore's law here. And you can sometimes use that extrapolations to look at what might happen and when you reach a tipping point, and then you know that things will change. So I started my career in the 90s, and my academic supervisor, he said that Moore's law will continue, but for physical reasons and density reasons, what will happen with the processors is that we cannot raise the clock frequencies all the time like we were doing really rapidly. They will cap out at like 3 gigahertz, 5 gigahertz, somewhere in that range. And then the transistors will be used for something else, and that will be multi-core processors. And I used that information about the forthcoming tipping point to steer my career. So I took more interest in like parallel programming and distributed systems and so on, and that has proven to be very useful. So this is an example of a likely, or a good prediction, something that likely might happen. We will use some extrapolation here in this presentation. We will also use 2 other technologies or techniques. One is to look at other disciplines that are ahead of data engineering in terms of their evolution. Look at what happened there and see if what the similar evolution is in data engineering. We will primarily look at software engineering in general and sort of back-end engineering as a prediction of how data engineering will evolve. And the easiest thing is that the future is already here. It's just unevenly divided. There are companies way ahead of other companies. There are decades in gap in terms of maturity in using data. So we can look at what the leaders are doing to predict. We will start by going way back in time to the 80s, one of the first digital hypes, which is called materials resource planning. And this is from manufacturing. And the process of material resource planning is that you would, if you were creating like custom goods, like metal goods or whatever, in a factory, you would take your orders for the month and you would carefully plan and optimize and say, okay, we're going to build these things and then we need to order these materials, and then you go to your suppliers and so forth. And there's a lot of, if you need to do this well, because that's where your margin is. And some companies figured out that we could do this in software. We buy an expensive IBM mainframe, and we could do this, instead of having people to do that for several days, we could like run the computation overnight. And this DuPont in the US and Black & Decker were early doing this. What happened then was that instead of, when people came with their orders and said, could you manufacture this for me? Instead of saying, well, you have to wait for a month and then we'll know if you fit into the planning, they could say the next day, well, yes or no. And of course, that makes a great difference. So that became one of the early digital hypes, and the other companies said, oh, these cool guys, they are having this software and doing cool things and doing much better than we do. We also want that software. So they bought the software, and then they did the resource planning with the software every month as usual. Right? So they took the new technology, but they didn't adapt the processes, and they didn't figure out how to use it well. It turns out that you need to change a bunch of things. You need to change your deals with your supply chain so that you get new goods, not every month, but every day and so forth. And we can laugh at this, right? And then we can go home and we can go to our work, and then we can go to our clients, which I do, and say, okay, we're in the cloud here, I would like a Kubernetes cluster. And they would say, yes, you go to the operations department and you ask for a Kubernetes cluster. Wait a minute, we have the cloud, we're supposed to be able to create this on ourselves, that's the whole point. Or at another client, we were constantly waiting for the network team to set up network connections, and they were like overwhelmed, so it would typically take a week that we had to wait, when in theory, you would be able to do this in the cloud. And we see the same happen with Agile and data, machine learning, and so forth. What is happening here? There's a management guru called Goldratt. He has written a book called The Goal. If you haven't read The Goal, please go read it. He studied these MRP, the technology change of MRP planning, and other technology changes. And he deduced these things. He was helping these companies, but it took him 20 years to figure out what the dynamics were for adopting these new technologies. And he concluded that you can benefit from new technology if and only if there's a limitation and the new technology removes that limitation or diminishes that limitation. And in order to benefit, you have to answer 4 questions. What is the power? What is the limitation that is now diminished or removed? And what processes and rules have we used in the past to manage and mitigate this mitigation? And what are the new rules that we now should use? How can we use this to predict the future? Well, the technology comes first. Then it takes decades for us to figure out these rules, just as with management resource planning. So if we can look at technology that exists or is about to exist, and then try to find the old rules and remove them, we can see what the future looks like. Are you following? And these old rules that we still have in place, like the ops teams that we have to go to instead of getting our resources in the cloud directly. This is a significant cause of waste in data engineering, and something that is really holding us back. We also need new rules. So for example, if you look back into the Industrial Revolution, we had steam powered it, and then eventually we got electrical engines. And that's a technology shift, right? And we know now that clearly electrical engines in manufacturing, for example, is much better than steam engines. But if we just take out the steam engines, put in an electrical engine, and the rest is the same, we're not taking full benefit. We can get full benefit, or more benefit, by realizing that the electrical engine is more powerful, more flexible, and so forth. But if we take electricity into a factory, we need new rules, otherwise accidents will happen, right? I'm not going to speak so much about new rules because that's essentially what yesterday's presentation was about. What rules have people applied in order to do efficient data engineering? So we're most going to look at the old rules today. It's a bit backwards, I know. We're looking at the future, we're looking at the old rules. First question. What is the power then of data engineering? Well, I have observed, I've been doing this for about a decade, and I've observed a number of things that are different in sort of modern data engineering environments, but not present in older. We can now store all the data. This is what Hadoop gave us. Before it was financially unfeasible to sort of store all the details in web-scale companies, at least. We can do cheap computations, and we can do more complex computations that we used to have. We can share data, and this is important. We'll dive into that later. And do quick experiments with data. And what's important here, with minimal risk. And I know that if I bring in data science and machine learning here and say, oh, what are these things giving us, then the scope goes out of hand. So I will stick to data engineering. Of course, data science and machine learning brings a whole lot of new powers. If we look into the most successful companies, we can observe a couple of things, which might say something about the future for the rest of us. One is that they are producing a lot more data things, data artifacts. In every data processing environment, you produce data artifacts or data sets. A data set is essentially a table in a database, for example, or a bunch of files. It can hold things like all of the sales transactions from yesterday, or all of the web impressions for the last hour, and so forth. And if we look at traditional companies, they and try to count how many data sets are produced per day, we have orders of magnitude like hundreds or thousands of them. And if we look at the very mature companies, we see several orders of magnitude. At Spotify, these are old numbers. It's probably in the millions today. And at Google, they're counting their number of data sets per day in the billions. And this is something that we know that the future will bring. I worked at Google 15 years ago now, and at that time, Google was clearly ahead in using, getting value from data and using data in comparison to what our typical Scandinavian banks and telcos are today. So there's still a prediction of the future there. And if you manage to bring the cost down, and you manage to move faster with data, you can get more value. And so in order to, in addition to bringing the cost down, we can also expect ourselves to be able to try new things out faster. And this is a little unscientific poll that I did. How long does it take you to change a trivial thing and along a data flow and get that passed through through your organization, crossing several teams? And you see here that the median time that I got in the response is like several months. But then there are some companies that are really fast in doing this. Again, difference in orders of magnitude in the ability to change things and try out new things. How does this translate to business value? What might we expect in the future here? And this is one of my favorite examples. I have it in almost every presentation. This is from a presentation of the people at Spotify that did Discover Weekly. And the interesting part is that they said that this, unlike what would have been required at many companies, this did not need a strategic decision with 50 engineers allocated to do this particular thing for like half a year. There were 3 engineers. They had access to all of the data in the company. They made an insight that perhaps this would be valuable. They built this first version in 3 weeks. The CEO said he didn't like it, but he couldn't kill it. That's not how Spotify works. So he just didn't give them any resources, but they launched anyway. 1 year after launch, there were 40 million active users on this feature. So it's one of the most successful machine learning features ever built in Europe. This is also, hopefully, what the future contains for the rest of us. Very, very few European companies can innovate at this kind of pace. So how are they doing these things? How are the companies pushing the cost of data processing down and having this agility and enabling people? One thing they have done is to industrialize data processing. In every value creation stream that we humans have, in history there has been a manual version where we sort of go into the woods and chop down trees with axes, for example. And then there's a mechanized version where we still do it manually, but we have power tools in our hands, so like a chainsaw, for example. Then there's an industrialized version. And one significant difference between the mechanized and the industrial version in most cases is that the intellectual work in the industrialized version goes into improving the process rather than doing the actual work. And there's orders of magnitude in efficiency between these variants. You can never compete with McDonald's, which is the industrialized version, in terms of efficiency. Even though you might like other food better, you can never compete in economic efficiency, for example. And you can never compete with IKEA, which is the far industrialized version of making furniture, with your local furniture shop, in terms of quantitative numbers. We've seen the same in IT, where we have gone from managing our infrastructure as craftsmen. When we wanted to change the way that our servers or network works or launch applications, we would SSH into the servers and we would do lots of configuration, change config files, restart things and so forth. We don't do that anymore. We have infrastructure as code where we change the process instead. We change the blueprints and then an automated process give us cloud resources. We have containers where we change the blueprints for application and automated process that deploys them and so forth. And this is where software engineering is head of data engineering. So we can expect the same thing to happen in data engineering. And this is what still only very few companies have done and gotten to this sort of fully industrialized mode of data engineering. And this is one of the factors behind the companies, both the sort of data mature companies, both pushing the cost down and generating many data sets and being agile and so forth. So the equivalent of this manual, mechanized, and industrial for data is from like Excel and calculators to the database and data warehouse age to the industrialized setting. This is the dependency tree for Spotify's old pipelines back in 2013. This is a time when they were producing tens of thousands of data sets per day. This is a couple of orders magnitude larger today. So if we go industrial, what does that mean for our ways of working? How will we work in the future? One thing that changes is data modeling. In a craftsman-like setting, if we do artisanal data modeling, we put careful work into ensuring that the data models are very well created and sort of future-proof. Because in a database or a data warehouse setting, once we have established the models, they are difficult to change. So therefore, there are some challenges that we have to prepare for. One such challenge is slowly changing dimensions, which is when you have sort of what you perceive perhaps as a static thing, like people's addresses, but they change every once in a while. So if you have a database table with people's addresses, and then you have their sales events, for example, and then you might think you can do geographic analysis by joining with the address table. But if you look at historical events, the address table is slightly out of date, right? So in order to handle this correctly, there are elaborate plans for how to do modeling, and we have star schemas, and we have satellites, and we have the data vault model, and so forth. So these data warehouse models become in what we call in operations pets. Like we create them once and then we nurture them carefully and they change slowly. This has been relaxed with the big data age, so this is much less of a concern these days. And if for people that are experts in this, you can see a certain annoyance and like, why are people so sloppy with this modeling? What has happened is the industrialization. And instead of creating a very carefully model artifact, or data artifact, which is still what most people are doing, at least the ones that work with data warehouse-based solutions and environments. We can shift, if we are fully industrialized, we can shift to working with a process that creates these models instead. And instead of reusing the model up here, we reuse the code that generates these models so that we can, depending on the use case, tweak this a little to sort of adapt to the use case. So for example, if we have an analytics use case for our e-commerce transactions, we might have one model that is really quick because we want results quickly. If we have a financial reporting use case, we might take into account other data sets, like for example, what we have deduced is fraud and so forth. But that might take a long time to produce, but that's more important for financial purpose or for reporting purposes. So we have a slightly different model and so forth. This change from craftsman work here to industrial process work here means that we can innovate fast on both sides here. So this is some company, the most data mature companies already do this, but this is very uncommon in most settings. So this is some kind of glimpse into the future by looking at what others are doing. So we look at, if we take Goldratt's questions and look at that view here, we can now compute things quickly. We used to have a limitation that it was expensive to create these models, and we had an old rule that we would apply all of this care, all of this data vaults and satellites and so on. So we can look into the future, and if we apply new rules that work well, which I covered yesterday, we can look into the future and see a world where these careful rules are removed, and that's how the future will look like. So that annoys some people that used to be really good at these things is perfectly on purpose. We do that to move quicker. This doesn't only apply to like data warehousing models, but also other data things that are created as pets, as carefully crafted out things. And one example is knowledge graphs, where it's common. Still, the most common way of creating a knowledge graph is to have a process which is half automated, half manual, and create the knowledge graph with an ontology which is shared throughout the company and viewed as the truth. In industrial environments, we instead make an automated process out of this and create slightly different knowledge graphs depending on the use case. We actually did this at Spotify now many years ago, where one of the core knowledge graphs is the metadata about artists, albums, and records and so forth. And we had gotten stuck where we needed to innovate on this part, so we took and make this shift. So I know that it works, but that's the only time that I've actually seen this happen in a while. Likewise with machine learning models, that's also something. If you read a blog post, data science blog post, here and here, you do these and these and these things, and now you have a model. Now you can sort of put it in production. That's a craftsman-made model, and the mature companies have industrialized this. Still fairly uncommon in most companies, and there's a good blog post by Google that sort of enumerates the different maturity levels for machine learning that essentially says what I said here, but in better words. So we've seen companies go through this journey, or the industry go through this journey from manual analytics and data handling to the data warehouse edge and to the big data edge. And this was fairly, or I wouldn't say it was easy, but those of us that adopted Hadoop early got a nudge here because of Hadoop's limitations. It is crap at some things. For example, indexing. You don't have any indexing, and you only have batch transformations to work with. So you have to sort of adopt an industrial process. Otherwise, you can't work with it at all. And it has so bad security paradigms that you have to share the data. So you get like the sharing and democratization for free. So we got nudged into these processes. We didn't understand it at the time, but it was a change of processes that actually was valuable. What has changed since is that during the big data hype, lots of companies tried this. They installed Hadoop clusters. They didn't get the benefits. You know, they installed the MRP software. They didn't get the benefits. Same story again. And what the vendors then did, the sort of data tooling vendors said, they realized that it's bad sales strategy to say, you can have all this cool technology, but in order to get value from it, you must completely shift the way that you're working. Right? It doesn't work as a sales strategy. So we've seen lots of technology that is like for democratization of data, easier ways to use data and so forth, and that's collected under the name of the modern data stack, where we combine new technology with something that looks more like traditional workflows. You can have like a Spark cluster, but it now looks like a data warehouse, and we call it the lake house. And that sells a lot better. This is a pattern that we've seen before. And so we can look at that time what happened. We've seen this in software engineering, right? We got the third generation of programming language back in the software explosion in the 80s. But there weren't enough software engineers. So there was a great need to find simpler ways to build software. And the response in the 90s was the 4GL languages, the graphical languages, and if we can program with UI, anybody can be a programmer. And we have low-code solutions and no-code solutions and so forth. These are now extinct. They don't exist anymore. Right? What happened is that they served a purpose back in those days, decades ago. But the solution was to educate people into software engineers, and that's now the most common profession, at least in Stockholm. So in the vacuum, they made sense. But now that the vacuum is gone for competence, and we have sort of raised the general level of software engineering, we don't need that anymore. So we have entered the 4GL phase of data engineering, where there's a vacuum. And these tools here, and by the way, have you seen that they look the same way? This is a 4GL thing from the 90s. This is Apache NiFi, which is a brand new low-code thingy. They serve a purpose, right? I'm not saying that they're bad, because they fill a vacuum. But they will go extinct as well, and we will educate data engineers if we are to believe that we follow the same pattern as in software engineering. So I'm saying that low-code and no-code things is a temporary thing and will die. How can I be so sure? Has low-code worked in other cases? It has actually worked in web development, right? It used to be really complicated, and you would have HTML programmers to do a web page, and they would have Emacs and neckbeards and all those weird things. But nowadays, we have things like WordPress and Wix, and it's really easy to do a web page. So it worked for web pages. Didn't work for software applications. Why wouldn't it work for data? I believe that the difference is the complexity in these things. Web pages is a mostly static thing. You can look at web pages and inspect them and say, well, okay, this looks good or bad just from the content, right? Whereas the behavior of software applications also depends on the user. So that's another degree of complexity, and the low-code, low-complexity things no longer work for building these things. Data applications has yet another degree of complexity. They both depend on the user behavior that interacts with the data applications, but also on the inbound data. So there's even a more higher degree of complexity, and I believe that the low-code tools will work even less well than they did for software engineering. There is an exception to the low-code tools. This SQL is the only long-term successful low-code language, right? And it's hard to argue with its success. It is used primarily for three things. One is interactive exploration of data, and this is really where it shines. It's fantastic for these purposes. The second is for backend applications where you need to retrieve something from a database, and SQL is the most common option. This works fine here, but that's such a simple scenario that it doesn't really matter all that much which tool that you're using. And it's also used for data processing, primarily batch data processing. So my claim is that it's not particularly long term. It won't be a major player here, even though it is today. The data processing is a complex thing. There are lots of complex business logic and high requirements on data quality and on testability and reusability and so forth. And these are a number of things that you might hope for a good programming language, a good language to express your business logic in. If we look at all of these, the SQL turns out to be really good in terms of learning curve because everybody knows it, but is worse than all of the other options, or the worse than the regular programming languages in terms of the other aspects that I could think of. So if you want more detail in why SQL long-term will not be the solution for data processing, there's a Twitter rant here that you can look up. So it will always be around because of the familiarity, right? Because people know it. But what I've seen in the most mature companies is that it is used for prototyping, but because of lack of composability and in particular data quality, it is not particularly common to see when things go to sort of sharp production and become important. Then the code is translated to other languages. This is I'll linger here for a while, even though I'm short of time, because this is a common a statement that I believe in that is commonly questioned. So I'll give you a little example here. I have approached SQL for data processing from another angle than most people. If you do it from scratch and you write your queries and it seems to work fine, the way that I encountered SQL for data processing was that at Spotify we were trying to find something to replace Python MapReduce with for good reasons. And we tried out SQL for a while. It turned out that the logic that we had, which was fairly complex, could not be expressed with SQL. It just wasn't sufficient, expressive enough with an existing mature pipeline. And this is an invisible wall that you strike into if you start from SQL, because you reach this wall where you can't do things anymore, and then you give up and do something else without realizing it's the language that's holding you back. Another thing that we couldn't do when we translated this pipeline was to carry our quality metrics and quality repairs on. So if you have a sort of a regular programming language, and use a tool like Spark or Hadoop MapReduce or something, there are tools for measuring quality, where if you deep down in the code have an if statement or a join, that, for example, that should match something but it doesn't, then that's a quality metric that you want to measure and perhaps correct, but at least get out as a metric so that you can monitor it and so forth. And this is easy to do in other data DSLs, but SQL doesn't really support this. And so instead, for each of these things, you have to have another SQL statement that is similar in size and complexity as the one that you have. And then as you have more and more of these, this just grows out of hand. So that's one of the predictions that I have, that low-code languages and SQL languages will not be long-term viable or long-term where we lean on. So how does this map to the 4 questions that we had? We had a new power to build more complex data processing flows. with the old technology, we used to be limited by what we could hold in our brains, but the big data technologies enabled us to scale further, and we used to mitigate the complexity here by applying low code and declarative languages. So if we lift that rule, we can go further into more complex languages. So I'm running out of time. I hope you will forgive me if I overrun by a few minutes. Sharing. One thing that big data did was to enable us to share data freely among inside the organization more efficiently. And that has, if we look at the 4 questions again, we now have the power to share data more efficiently, but this used to be difficult in a microservice environment because we had operational risk, we had governance risk, and so forth. So we had rules in place to mitigate those risks, and those rules were isolation and technical contracts between the different systems. And we could call these, like, we have a data product here that's hidden behind the rest, and we have a contract here, which is the API. And we're now seeing the resurgence of these old rules popping out, but in data lake environments where we say, it's not free for everybody to use. It's a data product that we supply and we provide a polished version of it. You're not supposed to look at the internals. It's up to us to provide a polished versions if you want to use it, and we have a contract in between to enforce this. This is also known as the data mesh. Will that survive or not? Well, I'm going to look at historics here again. This is from the original waterfall paper, where we had this separation of what people were doing, and in separate phases and different kinds of people and so forth. What we've seen in IT is that things work much better if we start bundling people together in the same team with different competences and work together towards a common goal, right? And extreme programming is such one example where we combine development and testing. Agile is another example where we combine requirements and design with the implementation and so forth. And DevOps, in DevOps we combine programming and operations, right? These have been widely successful and are likely to continue. So there have been in history lashbacks against these things where we just let these agile people loose and they create chaos. And one such lashback is the rational unified process where we say, no, we don't want this chaos. Now we need to again have these borders between people so that there are handoffs and there are contracts in between design and requirement and testing and so forth, and separate these people. So what does this have to do with data? Well, big data is yet another one of these lumping people from different disciplines together to work towards a common goal. And what we have extended this now to something called DataOps, so that we lump the operations together as well. And this continues and so forth with machine learning. So I'm claiming that based on history, the methodologies that go into the value stream and say there should be barriers here between people that do different things, and you should have handoffs between people along the value stream, are destined to eventually fade, because they essentially make us slower and slow down innovation. Whereas the methodologies that align us along the value chain and minimize the number of handoffs will be the ones that prevail. Based on that, all of those methodologies that we've seen have been successful so far. And I believe that this will go on so that we will see more solutions to some of the problems that we have, like compliance and governance and so on, by making people work together along those value streams and value chains, and integrate like compliance into the work so that it becomes a industrial process rather than manual thing, inspections and so forth. All right, I hope I have given you some kind of tooling to look into the future. Even though you might not agree with me, I hope that some of the reasoning and the glasses you got with the 4 questions might help you look into the future. I told you I would say what we're up to, and I think and believe that, or what I've seen so far is that changing the ways that people work is really, really difficult for companies, and that the methods we have to make our fantastic companies that we have here in Scandinavia adopt these things aren't working. So what we are doing is to try out a new collaboration method where we do industrial data processing as an external service, so that we have some control of the way we work, and we help the customer to work in the right way or not. Will it work long time or not? I don't know. In some cases we have reached the same efficiency levels as Spotify, for example. We're not at Google levels yet. That will require more investment. And our mission is to give these kinds of efficiency in working with data to Scandinavian companies. And what's driving me to do this is that I think there are so many companies that are great out there that I would like to, as a footprint of my career, try to help the companies that have values that I agree with. That's what I had to say. Thank you for staying over another few minutes.